Welcome to the second part of the presentation on epistemic inquiry. In this presentation, we're going to look at the methodology of how epistemic inquiry is taught. And in doing so, we will look at what are the 5 pillars of cognitive acceleration pedagogy. This comes from the so-called cognitive acceleration through science education, otherwise known as CASE, that was developed at King's College in the 1970s and 80s and further developed up to today. This methodology often starts with what's called concrete preparation, which is where some activities and discussions will be done to make sure that all the students involved in the learning are familiar with the terminology, some of the vocabulary, the materials that they're presented with, and a very concrete problem is set up. This often then leads to what's known as cognitive conflict. This will often be where questioning or some stimulus will be used to elicit the views of students about what the problem is, and there will usually be a difference of views. There will be some predictions that they make and explanations they put forward that don't actually get realized in the situation. This is a very, very powerful impetus for students to learn that their understanding of the world is not necessarily correct. A lot of these activities will be involved in small group discussion or whole class discussion, where there will be a lot of socially constructing of meaning and understanding. A very enhanced part of the cognitive acceleration methodology in epistemic inquiry is the idea of metacognition, where we have framing questions or we have discussions where we monitor the thinking that's been done, look at the predictions we've made, look to see how they fit with the observations or the observable reality that the problem situation has posed. Evaluating the difference between prediction and reality, starting to plan how we need to further develop our thinking. And a very, very important part is how can we bridge our understanding to new situations, to bridge to other models of explanation that we've created. So we'll see in the lesson simulation that's coming up how these 5 pillars of cognitive acceleration methodology are applied to real situations. Again, we will look at the 3 worlds of Karl Popper and how these can help us plan a lesson that will make an epistemic inquiry and create cognitive conflict, allow materials for social construction. And this lesson is an example of phenomena of freezing and melting. Remember, we have physical objects, our subjective experience of them, and the role of language in trying to move from subjective experience into scientific objective knowledge. In this case, the physical objects will be candle wax, ice cubes, and different material blocks. Our subjective experience will be, for instance, when we pick up these blocks, we will have certain thermal experiences and thermal perception. This will allow us to make qualitative observations, later quantitative, and a whole variety of language discourse and techniques of how to actually observe and measure freezing and melting. Later we will see that we try to resolve some of the cognitive conflict, some of the social construction that's going on, into creating an understanding through some kind of thermal models, some kind of thermodynamic system explanations of what's been observed. Okay, this would exactly be how the lesson would start. The first piece of concrete preparation is we have a variety of these different density blocks. We have some wooden ones, some plastic ones, and some metal ones. The metals including iron, brass, copper, and aluminium. And these would be passed around the class. And with just a very, very simple question of discuss what variables you experience when you feel these blocks, when you weigh them in your hands, when you listen to how they sound on the table. There'll be a whole variety of different things about heaviness, but one thing that nearly always stands out is the students will offer the idea that the aluminium and the copper, for instance, and the metals in general, feel cold, whereas the woods feel warm. Once we've done this, we will do some metacognition and social construction. The metacognition will be to monitor our thermal perceptions and discuss how we can achieve a consensus. And in general, this usually, with some prompting questions, leads to the copper feels the coldest. Some students dispute this and say, no, the aluminium feels colder, but either the aluminium or the copper are always the ones that feel the coldest. And one or two of the woods are chosen because they feel warm to the touch. I want you to think, what do you think your students would say? What kind of variables would they focus on? Then we move the concrete preparation towards a cognitive conflict, and this is a very, very common strategy, is the so-called predict, explain, observe, and then re-explain strategy. So here the very concrete preparation is using your senses about how warm the blocks feel. Predict what will happen when some candle wax, molten candle wax, is poured on top of two blocks. Here we're taking copper and wood. How quickly will this wax solidify or freeze? Often the use of the word freezing causes enough cognitive conflict. So you might say solidify or freeze, but allowing time to get over the idea that freezing is where something goes from a liquid state to a solid state. So I would give them 3 or 4 minutes to make their predictions and explain what they think will happen and why it will happen. I want you to stop and think, what kind of predictions do you think your students would make? And what kind of explanations of why their predictions would be true? We would give them time to do that. We would discuss and hear all of the predictions. Often students would be working with small whiteboards where they actually write their predictions onto them. This often is very, very important to make them really commit to their predictions and explanations. So later, when they've done the observations, we can monitor this cognition. We can evaluate how good the predictions and explanations were, and we can plan for the next moves. Okay, we would have done those experiments, and often then students, they'll feel that their predictions have been confirmed, because it looks like the wax will freeze very quickly on the copper, because the copper is cold, many of the students will say, and it doesn't freeze as quickly on the warm wood. And there they seem to have a lot of confirmation of their views. Now we move on to the second episode of this. Again, they use their senses. That you might give them the blocks again and say, okay, are we all sure that the copper feels cold and the wood feels warm? I want you again to predict and then explain why. What will happen to the ice blocks when ice are put on top of a copper block when ice is put on top of a wood block, how do you think the rate of melting of the ice will be? And explain why you think that will happen. And again, we give the individuals and the groups time to do some social construction, to discuss, to write their predictions onto the small whiteboards or note paper, whatever you're using. And then we actually give them a method. You don't necessarily want to move straight to this quantitative method, where this oasis foam that we use to stick flower shoots into is very, very useful here, because it will soak up the melted ice, the water that comes from it, and we will be able to actually get a quantitative rate of melting. The spaghetti is there, or you can use toothpicks, just to make sure that the ice block doesn't slide off the metal or the wood block. Here's an example of 4 different blocks. We have copper, aluminium, one of the plastics, and wood. And this is over 10 minutes. And during this time, I ask the students to feel the blocks, not to feel the ice, but to feel the blocks. And this creates even more cognitive conflict when they see that the block that feels the coldest, the copper, appears to be melting the ice the quickest. This is a very huge cognitive conflict. And at the end we can see very clearly how the copper seems to have melted into the ice block, leaving a large amount of measured melted water. Aluminium has had a similar effect. Okay, this leads to a lot of cognitive conflict and discussion, and in the final part of this we're going to try and enhance this cognitive conflict. For instance, by saying, well, okay, let's go back to your feelings of the different blocks and let's see actually what their temperatures are. And what we observe is that all of the blocks, when you stick and maybe for 10 seconds with a little piece of tape, that all of the blocks are 22 degrees, which actually is the temperature of the room. And this is a major cognitive conflict, the difference between what the temperature is and what the felt temperature of the different blocks. We can also then measure that the wood block, during the time when the ice is on it, seems to only cool by a very small amount, 20 degrees, whereas the copper has reached 3 degrees. And we would make sure that all of the students understand these sets of quantitative observations and ask them then to say, okay, we now need to look at the observations we've got. We will spend some time monitoring what our predictions were for the wax, for the 2 different blocks, what our predictions were for the ice melting, and also now the information we have that during those processes there was temperature differences between the blocks, and the paradox that the coldest block seemed to be melting the ice the fastest. We need to try to get all of these observations and explain them in some kind of new model. This is where I would give out these laminated sheets showing these, so that the students can use board markers on the acetate sheet to actually add their ideas as to what's going on. At this point, we would scaffold them to say that, well, okay, what exists in a thermal system? because up to now they've been very, very focused on the wax, the blocks, and the ice and the blocks, and very, very few students would focus on the ambient conditions. That's the boundary of the room and the air in the room. And we would push them if they don't come up with this in their system, because it's clear that the air plays a major role. Now, to help scaffold this, some activities that we've developed are, let's go back to the original start of your thermal perceptions and completely hold the copper block in your two hands, in the palms of your hand, close together for a minute, and then see what do you observe, how does the copper feel, and then do the same with the wood. And remarkably, the students then focus on the idea, okay, the copper block felt cold at first, but then after a while it started to feel warm. It felt the same temperature as my hands. And in fact, it cooled my hands slightly, but actually the copper block then became warmed by my hands, where the wood block appeared not to be. And then you let them put the blocks down and come back to the block and say, okay, the block then appeared to cool down again because it became the room temperature. Also, another scaffolding question that helps a lot of metacognition is, if we had no blocks and just put the ice blocks on the table, what would happen? And of course, all the students would say, after some time, the room would have melted the ice blocks. This leads us to be able to start developing a model through this inquiry into our thoughts, into our own predictions, into our understandings, of building a model of heat transfer from warmer objects to colder objects, which is a fundamental step in developing a scientific understanding of heat transfer.